Good morning. Today we will tell about the crystalline defects in structure. The physical properties of an ideal crystal is determined by its chemical composition, bending forces between particles, and the crystal symmetry. That is, categories, its symmetry classes. These properties are called structural and sensitive. These included magnetic, optical, piezoelectric effect, and etc. But in real crystals, many properties depend largely not only the type of crystal structure, but also on the defects of this structure, the frequency of violations and balance. These properties are called structural sensitive. This, for example, ionic or semiconducting electrical conductivity, luminescence, ductility and strength, color of crystal, process of crystal growth, plastic deformation, diffusion, and etc. Structural defects are caused by several reasons: thermal vibrations of atoms and violence of the electron density, the impact of any radiation, temperature rise, etc. All structural defects by geometrical phases can be divided into the following types: pointed point defects in violation of the periodicity of isolated points of the lattice. All three dimensions do not exceed one or more interatomic distances. Point defects are a vacancy, the atoms in the intersides of the atoms are aligned sublattices, and impurity atoms. Linear defects, one-dimensional, that is, extended in one dimension. A violation of the periodicity extends to distances comparable to the size of the crystal, while in others it doesn't exceed several lattice parameters. Specific linear defects dislocations. But there are another linear defects, such as chains of linear defects or point chains or point defects. And the third group, surface defects. Surface defects extend in two dimensions at a distance comparable to the size of the crystal. And the third one makes up some of the parameters of the lattice. These are the twin plane, the grain boundaries, and block stacking. And at last, the volume defects. These are voids, pores, particles of another phase inclusions. We emphasize again that all these defects are produced during crystal growth or as a result of various influences and significantly affect the properties of the crystal. We will begin the simplest crystalline defects, the point defects. The point defects is a line of the crystal structure whose dimensions in all three dimensions are commensurate with one or several interatomic distances. Please look here. A point defect can be simple and complex structure. Simplest point defects, the vacancies of atom or ion at the lattice side. Embedded or in situ atoms and ions which are located on the illegal place between the nodes. Interstitial atoms may be both its own and impurity. Here, complicated point defects. Vacancies can be combined in D vacancies, 3 vacancies, vacancies, etc. I have already talked about it. The clusters of many vacancies called clusters form poles and voids. Point defect can move through the crystal, interact with each other, forming various neutral combinations. The most effective neutralization is neutralization of point defects by the formation of pair defect, Schottky defects, and Frankel defects. For example, a pair of cation and atomic vacancies meeting with each other forms the so-called Schottky defect. It is often found in alkali halide crystals. The presence of the Schottky defect reduces the density of the crystal since the atom that formed the vacancy diffuses to the surface of the crystal. The Frankel defect is a vacancy and a positively charged atom in the interstices. Defects of this type prevail in crystals such as silver halides, argentum chloride, argentum brome, etc. Frankel defects are also usually formed in crystals with a diamond structure. These defects don't affect the density of the crystal. In general case, the crystal can contain both Frankel defects and Schottky defects, with those predominant that require less energy to form. Also, complex specific point defects are Kohler centers. The Kohler centers are complexes of point defects that have an intrinsic absorption vacancy and accordingly change the color of the crystal. The Kohler centers differ in the wavelengths of their own absorption and the position of their own level in the forbidden zone. The electron sense give levels above the middle of the forbidden zone. The Hall centers give lower ones. The simplest of centers of coloring is the F center. It consists of an anionic vacancy which acts as an effective positive charge. It keeps a free electron supplied, for example, by an excess atom of an alkali metal as a result of its ionization or introduced into the lattice by an impurity atom. The F center causes appearance of adsorption bands in the visible region, as a result of which a colorless crystal becomes colored one. There are other models of colored centers. V center consisting of a cation vacancy and the whole. R1 center, which is an F center plus ionic vacancy. M center of F center plus anion or cation vacancy. Complexes composed of point defects and impurity atoms differing in their valence from the atoms of the main crystal are even more complicated. Introduction of such impurity atoms into the crystal also changes the concentration of the intrinsic point defects of the crystal. Of course, the point defects depends on the properties of crystal. What is this effect? The first, as noted above, point defects have a very large effect on the many properties of the crystal. These include the first, density. Density of the material decreases with increasing vacancy concentration. Diffusion in crystals is carried out in such a way that the diffusion atom moves in a certain direction by jumping to vacant places of the lattice. The zone process can be considered as a drift of vacancies in the opposite direction. The injected atoms and vacancies deform the lattice. and therefore a smaller energy is required to create a vacancy next to the implanted atom intrinsic or impurity than to form it in any other part of the crystal. Therefore, the vacancy interacts with the diffusion atom. The second, electrical conductivity. Electroconductivity is particularly strongly affected by impurity atoms. In semiconductor crystals, charge is transported by the motion of electrons carrying a negative charge or holes carrying a positive charge. In very pure crystals, the number of conduction electrons, N, is equal to the number of holes, P, and only intrinsic conductivity exists. In a purity semiconductor crystals, condition where condition N is equal P is violated and the conductivity is sorry, one moment. Where the conductivity is determined by the concentration of impurity point defects and their valence structure. Excess valence electrons contribute to N-type conductivity and excess holes contribute to P-type conductivity. Therefore, in semiconductor crystals, impurity atoms have a particularly strong effect on the electrical conductivity. For example, introduction of one boron atom into 100,000 silicon atoms increases the electrical conductivity of silicon by a factor of 1000. The third, ionic conductivity. This kind of conductivity is determined by a motion of charge point defects, vacancies, interstitial intrinsic of impurity atoms. In the absence of an external electric field, there is a certain probability of moving an ion from a lattice side to an adjacent vacancy, but these displacements are random and undirected. If an electric field is applied to the crystal, the ions of one sign, for example cations, move in one direction, and the vacancies corresponding to them and move in the opposite direction. Therefore, the value of concentrations of vacancies and impurity atoms can be measured from the value of the following current. Of course, we are used to do it. Look the short film using this reference, please.